Okay, so since it's recording now, again, do you see that it's recording? Do you have any indication that it's recording?
Yeah, we see.
Not sure where do I see that on my screen, since I'm sharing my screen. Okay, anyway, so again, we have two observers, the blue and the red. They are both looking at an object, right? And each one describes the location of this object using his or her own coordinates, right? Now, generally they disagree, right? On the coordinate in which this object is at, right? But, you know, it doesn't mean that anyone is wrong. Each one is right in their own frame. Now, Michelson and Morley says that, you know, if we have a light crest, and since the light moves at the speed of light, and if the source of light was somewhere at the origin, right, t equal x, y, z equals 0, and t prime equal y, x prime, y prime, z prime equals 0, right? Then the crest of the light, right, after some time t will be described by the blue observer as x squared plus y squared plus z squared equals c squared t squared. And by the red observer, it will be x prime squared plus y prime squared plus z prime squared equals c squared t prime squared. This is what Michelson and Morley said, right? That's essentially what it means. And from that, we deduce, right, that although the object, the two observers will disagree on the location of an object, on the coordinate which specify an object, they will agree on the interval between two events, right? So we have two events, blue, I don't know, green and another green, purple. Green and purple, right? Each one is described by the coordinates, right? But the interval between these two events, right, which is delta s squared, is defined to be minus c delta t squared plus delta r squared, or delta s squared is minus c delta t squared plus delta x plus delta y squared plus delta z squared. Right, I have a delta here, so it's between two events. Both observers agree on that. This is a direct consequence of the Michelson-Morley experiment. This is the heart of special relativity. Right? Interval is conserved. And as we saw, we gave the example that it's very similar to the distance between, you know, in three-dimensional or two-dimensional Euclidean space. Now that we understood that, we started to do some compactification of the notation, right? So again, two things to remember right now, three things maybe. One, right, we never mix coordinates. Either we work on the coordinates of O, or we work on the coordinates of O prime. But you cannot mix. Two, we're speaking of an event, right? That's going to be very, very useful to you, to everybody that does special relativity, because things get really confusing. So when things confuse you, you just think of an event. You speak of an event, okay? And three, we said that the interval is conserved quantity. Then we started to compactify the notation, and we said, okay, rather than working with t, x, y, z, we work with a 4 vector called x mu, such that x0 is just ct, x1 is just x, x2 is y, x3 is z. So mu goes from 0 to 3. Then that's a standard notation. Then mu is an upper index. Then we introduced the matrix, which we call the metric. It was a very simple matrix. We have it with Greek letters with two lower indices, eta, mu, nu, which we wrote as -1 and then 0, 0, 0, 0, 0, 0, plus 1, 0, 0, 0, 0, plus 1, and plus 1. So everything which is not on the diagonal is a 0. And on the diagonal, it's a -1 and then 3 pluses. Okay, and I said that if any of you will do particle physics anytime, the metric appears there as well, but with a minus sign. So eta mu nu particles is +1, -1, -1, and -1.
Asaf, shouldn't it be -1 on the bottom right corner?
No.
Isn't it -1 +1 +1 -1?
No, it's a minus plus plus plus.
Okay, so I think
Time,
last time we said it wrong, or maybe I copied wrong.
Likely you copied it wrong. It's a minus plus 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 time x, y, z. Okay, and then in particle physics, it's the opposite. It's plus, minus, minus, minus. And then using that, we compactified the notation and we wrote down the interval delta S squared as sum over mu and nu from 0 to 3, both of them, of eta mu nu delta x nu delta x nu. And what's written here is the same as what's written here. It's the same. And then we said, okay, now we're going to use Einstein's summation convention, which states that every time we see an index in the same side of an equation, once as an upper index and once as a lower index, we understand that we're summing over this index. So it's called a dummy index. So we don't need to write down the sign, the sum. Because it's understood that that's what we're doing. So it's really written here, eta mu nu, delta x mu, delta x nu. And I told you that if you get confused, every time you're seeing an index that appears twice on the same side of an equation, once as an upper index, once as a lower index, you can simply add up the sum. The same index cannot appear twice on the same side of an equation as twice as an upper or twice as a lower. That cannot be. If you got that, that means you did something wrong in the math. Okay? It can appear on the different side of equations, of course, but not on the same side of an equation. Okay. Now this is called the Einstein summation convention, and the indexes that appear twice on the same side, once as an upper index, once as a lower index, are known as dummy indexes. Okay, so here, mu and nu, dummy indexes. With these definitions, we did define a Lorentz transformation. It's a transformation, right, from one coordinate system to the other, from the O to the O prime, which conserves the interval. So we said one example is translations, right? Translation x mu goes to x mu prime, which is x mu plus some constant n mu, right? Mu goes from 0, 1 to 3, so it can be translation in time as well. This is just a shift of coordinate of the origin of coordinates. right? The other thing is some rotation. In rotation, the only other linear transformation is to multiply this for vector x mu by some matrix lambda mu prime nu. So we write down x mu prime is just lambda mu prime. Again, remember the notation. There is a space here. It's not one on top of the other. They are diagonal times x nu. And we derive the condition for this matrix lambda. Lambda is a 4 by 4 matrix. And we saw that the condition is that eta rho sigma lambda mu prime rho lambda mu prime sigma eta mu prime mu prime. This is the condition on the matrix lambda in order for it to fulfill, to conserve the interval. And then we gave two examples, right? We said that one example is rotation, right? Lambda mu prime nu, 1, 0, 0, 0, 0, 0, 0, cosine theta plus sine theta, 0 minus sine theta, cosine theta, 0, 0, 0, 1. Rotation in the XY plane. Right, remember what we have here? Time x, y, z. So when we're transforming from one coordinate system to the other, rotation do not change the time, right? So t prime is equal to t, it does not change the z. Z prime is equal to z. It does change the x and y. X prime is x cosine theta plus y sine theta. Y prime is minus x sine theta plus y cosine theta. You've seen that. And we said this is a legitimate Lorentz transformation. And then the other type of transformation is called boosts, which I really view as rotation where time is one of the axes. Right, so e.g. t and x plane looks very similar, only because we have this minus sign, then we replace the cosine and sine with the cosine hyperbolicus and sine hyperbolicus. Lambda mu prime nu is cosine hyperbolicus of phi minus sine hyperbolicus of phi, 0, 0. And then we have this extra minus sine hyperbolicus of phi, cosine hyperbolicus of phi, 0, 0, 0, 0. And then the y and z are not being touched. Right? Again, t, x, y, z. Y prime is equal to y, z prime is equal to z, but t prime is equal to cosine theta, cosine hyperbolicus of phi t minus sine hyperbolicus of phi x. And again, we proved and we showed, well, not completely, but we showed that this is a Lorentz transformation. Okay. Now, so far what we did was completely math. Right? The only physics was here. This was the physics part. Everything else was pure math. And then towards the end, I showed you that, you can actually associate, actually write down the timeless hyperbolicus of phi. You can write it as beta. And then this transformation ends up, and then gamma, right, is 1 over square root of 1 minus beta squared, definition. And this is also a definition. And when you do that, you end up that this transformation is in fact identical to the transformation that you already seen when you were young, in kindergarten. Ct prime is equal gamma Ct minus beta x, and x prime is equal gamma x minus beta Ct. We actually proved that. And then the last thing I did was going back to some physics where we discussed time dilation. Right. Then I introduced the concept of proper time as a minus delta S squared over C squared. Proper time is the time as measured by a clock that is not moving with respect to me. It's my biological clock. It's the clock that is attached to my hand. Now you may see me and my clock move. But when I look at my clock, even if I move, I don't see the clock moving. Right? This is the proper time. Right? And of course, according to me, since the clock is not moving, right? Or we can simply use that, write down delta tau squared is minus 1 over C squared delta S squared. We wrote it down right here. Eta mu nu delta x nu. Eta mu nu delta x nu. Right. And then you would see my clock moving with some velocity v. So observer the prime is the clock, same clock. Goes at velocity v. Yeah. So by time interval delta t prime, again, this is the second observer. So he only sees or she only sees delta t prime, not delta t. Because delta t is me. Delta t prime is the second observer. Delta t prime at delta t prime, the space interval is delta x prime is v delta t prime. And so the proper time, delta tau prime, is delta t prime squared minus delta x prime squared divided by c squared, 1/2, which is just 1 minus beta squared, 1/2 delta t prime. But now we use again the fact that the interval is conserved. And so conservation of the interval means that delta tau prime must be equal to delta tau. So the O prime, which is the clock in motion, we also see that delta t prime is equal to 1 minus beta squared minus 1/2 times delta t, which is just gamma times delta t. So whenever you see the clock in motion, you see the clock ticks more slowly. Where do we see that? Well, for me, the easiest way to always remember that and not get confused is the fact that cosmic rays are observed at Earth, although their lifetime, very energetic cosmic rays, are observed at Earth, although their lifetime is very, very short, because they're very energetic. So they shouldn't be seen, they should decay very quickly, but we still do see them. Okay, this is as much as we did last time. So before we start today's lecture, then I want to stop and ask you if you have any questions. No questions? Everything is clear? Okay, everything is clear and everything is clear. So I promised you we're going to be the edge between math and physics. Right now we're going to do some math so that we can proceed next time with the physics. What we're going to do now is to introduce vectors and tensors. You know, a lot of physical quantities are vectorial quantities. Velocity, acceleration, right? So we need to get a precise definition of what are vectors so that we can actually work with all these physical quantities first. So, well, you've been using vectors for many years now, I believe, or at least a few years now. What is a vector? You've been using it, right? I don't know, you learned vectors in high school, no? I don't know.
Magnitude and direction.
Magnitude and direction. Yeah. That's a bit problematic. Why is that problematic?
You need a frame of reference to say in which direction it is compared to.
You're right that the problematic notion is direction here. You're right that we have some problem with defining what is a direction. We're going to have to spend a lot of time about that. But yeah, normally, you know, you draw a vector as a directed line segment, right? Or object with magnitude and direction. So, you know, in 4 dimensions, obviously it's going to be a 4-dimensional object, right? So we call them 4 vectors, right? So in 4D, Minkowski space, so we should write it down. Like Minkowski space, it's 4D. So we have 4D objects, which are denoted as 4 vectors. We're going to use this terminology, 4 vectors. If we just use the space, then we're going to call it just regular vectors. Okay, we've seen one 4 vector. What is this 4 vector that we've seen? There's only one that we've seen. What is that?
The X that we see.
Location, right? The position, right? Or the coordinates. So we see a space-time coordinates, space-time coordinate vector. Right. CT, X, Y, Z, which we call X with an upper index mu. Okay. Now here is my definition of a vector. So the quantity which has a magnitude and direction. I cannot use that because I don't have a notion of direction. You'll see in a few minutes why I don't have a notion of direction. So what I'm going to define a vector according, does anybody, but before I say the answer, does anybody want to have another guess? Well, how am I going to define a vector?
Maybe with the dot product it has through its basis vectors.
I said the dot product and you say basis vectors. I didn't even say what are basis vectors. And I didn't define what is a dot product. So we're going a bit too fast now. Okay, a vector, right, is defined as any object or quantity whose components undergo the same transformation as the coordinate system. Again, so definition. Right. The 4 vector is any quantity whose components undergo the transformation V alpha goes to V prime or V alpha prime, so is equal to lambda alpha prime beta V beta when the coordinate system is transformed in the same way. X alpha goes to X alpha prime equal lambda alpha prime beta X beta. The key is this word, whose components. What happens to the vector when I change the coordinates? What happens to a vector when I change coordinates?
Nothing. Only its representation changes.
Nothing. Very good.
I changing.
Very, very good. I don't know who said that?
Me.
Very good. Excellent. A vector is an abstract quantity. It doesn't care. The coordinate is something which we use to describe it. We have to have a basis, right? And we describe the components of the vector in that basis. We change the basis, we change the components, but we don't change the vector. Okay, this is the definition of a vector. Now, in fact, I was a bit lying to you because this is not exactly a vector. The precise name is called a contravariant Orbit. There's a contravariant Orbit. That's the exact name for what I just defined here. Right? Now, what do we need to know about this contravariant, this abstract object, contravariant 4 vector? So first, we already said, right, it has 4 dimensions, right? The dimensions is 4, not 3 or 2 as in Euclidean space. The most important property is that the vector belongs to a point. Okay? Each vector is located at a single point. A vector, you know, we normally denote vectors with arrows, right? So sometimes people get confused and say, okay, so I have here, I'm putting a vector here. So a vector connects the origin to the point O. No, that's a misconception. A vector belongs to a single point in space-time. Each vector is located at a given single point in space-time. Right. It's going to be crucial when we're going to discuss curved spaces. Right? You don't see that in Euclidean space because Euclidean spaces are flat. It's not going to be even crucial in Minkowski space, but it is going to be crucial when the spaces will become curved. Okay. Now, okay, so we said it has 4 dimensions, and we said it's located at a given space-time. It's a given point in space-time. Okay, the correct way to think of it is the following. I'm going to draw a 2D curved space. This will be my 2D curved space. Then the correct name to call it is a manifold. This is a technical name. It's called a manifold. This is denoted as M. And then I choose a point on that manifold, P. Right? Now I can think of the set of all vectors that are located at this point on the manifold. Go through that point. I'm going to continue to draw vectors with arrows. That's fine. Right? So the set of all points form a space, which is called, does anybody have a name? Have any idea? Or to throw an idea? That's called the tangent space. Basically, it's like taking a flat plate and attach it to the manifold at the point P. That's called the tangent space. And it's denoted by TP. Again, think of a ball, right? So at every point along the ball, you can put a piece of paper attached to it at the surface, but it's going to be only at that point, right? So all the vectors that will pass through the point P at that point will be in that 2-dimensional, flat space, right? This is the tangent space at P. Of course, if you go to a different point, it's going to be a different space. Right? Again, think of a sphere. You have a sphere, attached to it flat space, right? This is going to be the tangent space at TP. Okay? Yeah. Here. So the set of all vectors that are attached to that point P form a space. This is called as the tangent space at P, the set of all vectors at a point P on the manifold, basically it's a curved space-time on a curved space-time. They form a plane. Which is tangent to the point P. Right? That is called tangent space. Call it TP.
Okay. You can define a vector only in a flat space, right? And you have a curved space, so you define a flat space attached to this curved space where the vector lives in.
I define a tangent space at P. And I said that a vector belongs to the point P. Essentially, I'm defining a tangent space there, right?
Which is it's always flat. It's a plane, right? It's always a plane.
Plane, yeah. But I said that basically the correct way of looking at it is saying that set of all vectors at point P form a space. This is a tangent space. What I'm showing here is an illustration of that. Of course, this is what's the dimension of the manifold M that I draw?
Two-dimensional.
Two-dimensional. Of course, I cannot do it in four-dimensional. This is an illustration. I want to avoid the use of the word flat here. Though I think you can, but I want to, this is something which is subtle, so I need to think a little bit if I'm allowed. The correct way of thinking of it is to say, okay, the set of all vectors at P form a space. This is the tangent space, and this is how it would look like. Essentially, it will be flat, but I need to think if I'm not limiting myself here to something which I shouldn't do. Likely there is no problem because we do physics, we don't do math. And what we do in physics comprise of nice manifolds, infinitely differentiable, things of that kind. So we don't have spikes. It doesn't look like a porcupine, right? It just looks like a nice and flat manifold. So mathematicians might not like it, but I'm a physicist, so maybe I can say that yes, it's flat. Okay. So the correct way of thinking of it is that at every point P in space-time, we can always construct a tangent space, which is called TP, right? And this is basically an abstract vector space, right? So TP is an abstract vector space. And the vector space is something which I believe you know from your first year linear algebra, right? Yeah, that's easy, right? So very roughly speaking, for those of you who need some refreshment of memory, right? What is a tangent space? What vector space, sorry, right? So a vector space is simply a collection of objects, right? Collection of objects. Namely vectors, right? Which can be added together and multiplied by scalars, right? Real numbers. Multiplied by scalars, right? Simply real numbers. Right. So any two vectors, if V and W belong to TP, right? And A and B are real numbers. Then we have that A plus B, V plus W is just AV plus BV plus AW plus BW. It's the same linear algebra you know from first year, right? Right. Of course, like every vector space, there is an origin. So meaning that there is a zero vector, which essentially functions as the identity element, right? So there is a zero element, so V plus zero equal to V. There exists a zero vector, right? And in vector spaces, which you've seen, you know, there are additional things, you know, inner product, etc. But we actually don't need that for now, so let's forget about it. Just that you know that it says that there is this vector space. So far, so good. Everything clear? Yeah, good. So let's speak about basis for vectors and the components. So as we said, it's often very useful to decompose any vector, which is abstract, into its components. But these components are only relevant with respect to some set of basis vectors, right? What is a basis? What is a basis, guys? For a vector space?
A set of vectors from which you can build all other vectors?
Right. No, it's simply a set of vectors. Basis is a set of vectors which, right, needs to do two things, right? The first one is to span the vector space. Namely, every vector, right, can be written as a linear combination of basis vectors, right? What's the second requirement from a basis? One, it spans, and what's the second requirement?
Vectors should be non-linear.
What?
Orthonormality, perhaps?
Doesn't have to be orthonormal, no. It has to span. What's the other requirement?
Orthogonal. They have to be orthogonal.
No, they don't have to be orthogonal.
No.
Forgot your linear algebra?
Supposed to be minimal or something?
Yes, thank you. Right, linearly independent. Right. Right. So no vector in the basis can be written as a linear combination of other basis vectors, right? Now you know that. Yeah, okay. So for a given vector space, how many bases one can think of?
Infinite, I guess.
Infinity, right? For a given vector space, there's infinitely number of legitimate bases, right? They don't have to be orthonormal. They can be many things, right? I can span this 2D, right? I can have these two vectors as a basis, but I can also have these two vectors as a basis. That's perfectly fine. They're not orthonormal, but they're basis. Right? They're two and they're independent, right? This is also legitimate basis. It's also basis. Also, this is a legitimate basis. But these are all legitimate bases for this two-dimensional space that I'm having right now, right? So we have infinite number of possible bases, of legitimate bases, but there is one thing in common to all of the bases that I can think of, and that is, what will be common to all the bases?
The amount of
Oh, you
vectors
just
in
said?
the set.
Thank you, yeah, right. The same number of vectors which form the basis. How do we call this set number of the number of vectors which form the basis?
Dimension.
The dimension of the space, right? So you know that, right? There's nothing new right here, right? So so there is infinite. There are infinite number of legitimate bases, but each basis has the same number of vectors, which is the dimension of the space. Right. So obviously for the tangent space associated with the Minkowski space, the number of vectors is 4. Now, that's the first thing. The second thing, which is crucial to have in mind, although you said it rightfully, right? A vector is perfectly defined by itself. I don't need a basis to define the vector, right? So the basis is used to decompose the vector into its components, right? But the components are with respect to an arbitrary basis. When I'm changing the basis, I'm changing the components, but I'm not changing the vector, right? A vector is perfectly defined by itself, regardless of its decomposition into components with respect to any arbitrary basis we may choose. That's important because it's very confusing, right? This is my vector. Now I can think of one basis. I want to change color, right? And this will be my components of the vector, right? In that basis, x1 and x2. I can think of another basis, x1 prime, and x2 prime, and the components of the vector in this different basis, x1 prime and x2 prime, right, are going to be different. But that doesn't mean that something happened to the vector. It just means that I changed the basis, right? So, you know, the use of basis is really helping us, right? But that's it. It's aimed to help us, no more than that. So is that clear? Yeah, okay. So let's look again at the tangent space TP, right? So we can set up a basis of 4 vectors, which I denote. So let's look at TP now. Consider TP, right? So the basis of 4 vectors I'm going to call it E and with a mu and parentheses. It's a quite subtle notation here, right? Mu is, you know, CT, X, Y, Z, or 0, 1, 2, 3. Right. Now, we normally don't want to, you know, make our life miserable, so we simply choose the basis vectors to be aligned normal to the coordinates, right? X mu. Right. So E1 is normally along the X1 direction. Right. Now have in mind, this means that we're talking about 4 different vectors, right? E mu. So 4 different vectors. It's not the same as 4 components of the same vector, right? That's why I use the parentheses. These are 4 different vectors. It's not the 4 components of a single vector, right? 4 different basis vectors, right? E1, E2, and E3. So we said that a vector A is written as a linear combination, right, of the basis vectors, right? So A, any vector, can be written as A is A mu, right, in that basis, E mu. Right? Remember, this is simply sum from mu goes from 0 to 3 of A mu, E mu. But don't get confused by the notation. right? A mu would be the components, E mu set of 4 vectors. Now, as you noted, I wrote the mu index for the E mu as a lower index so that I can use the Einstein summation convention. Right? Questions? Okay. So obviously, if I choose a different basis, then the components of A have, different values. A will have different components, right? When I change the basis, right, what happens to the transformation? How do I change the transformation law of the components? Well, I wrote it down to you right here when I define the vector. When I change the basis, I need to change the components of the vector. Right? So how it works. I mean, it's a bit abstract, but just that you get a feeling of how these things work. How do I choose a basis? But we'll discuss that more thoroughly later on when we discuss general relativity. Right now, I'm giving you the basic structure. It's really just the basic structure so that we can proceed on with the physics. Okay. So the standard example is what known as the tangent vector. So example for a vector space. Or for vector in general space-time is a tangent vector to a curve. Example of a vector. It's called the tangent vector to a curve. Again, we have a manifold M. There is a point P on the manifold, right? And then I take a curve which goes along the manifold, right? This is a curve. And it goes through P, of course. It's on the manifold, right? Each point on the manifold, right? Now, I can specify the coordinates as a function of 3 parameters along the curve, right? So for example, I start by specifying how do I know where I am along the curve? So I put some parameter, call it lambda. So, lambda equal to 0 is here, 1, 2, 3, 4, whatever. There is a path that goes along the curve, which is specified by some parameter lambda, right? And the coordinate, right, is a function of this 3 parameter, right? So x mu is x mu of lambda. That's true along the curve. So what are the components of the tangent vector? What will be the components of the tangent vector here? The tangent vector to the curve.
The derivative?
The derivative. Very good. So V mu is just dx mu over d lambda. Who said that?
Me.
Very good. Very, very good. And the vector, right? We can write the vector as V is equal V mu E mu. This is the full vector. Right. Now, when we do a Lorentz transformation, right? What happens to the coordinates? x mu under Lorentz transformation. Right? Under Lorentz transformation, x mu goes to x mu prime, which is, right, lambda mu prime nu x nu. What happens to lambda?
Nothing.
Nothing. Lambda goes to lambda. So what happens to v mu? The components? They will undergo the same Lorentz transformation as the coordinate.
Saf,
Yeah.
can you explain again the meaning of lambda?
Oh, it's just a number that specifies where I am along the curve. You can simply think of a line, and you want to know where you are along this line. It's a 2D here in this example. Right? Free space. Two-dimensional space. This is the path. I know that I'm somewhere along this path, but where along this path? So just say, okay, here is lambda equal to 0, lambda equal to 1, lambda equal to 2, lambda equal to 3, lambda equal to 4, lambda equal to 5. Now you can call me, where are you, Asaf? I say, oh, I'm at 5. Then you know where I am. You know that I'm somewhere. I mean, I'm here, and you're here, and you want to meet me. That's it.
Okay.
Okay. Good. So this is a general 4-vector. We'll get back to that even more in depth down the line. But right, as I said, I use this notation of the basis vectors with a lower index, right? Because I wanted to use the Einstein summation notation. Right? But that means that, you know, and I'll just show you that if I take V as a tangent vector to a curve, then it is going to be, it's a real vector, right? It transforms the same way as I defined the way a contravariant vector should transform. But that means that when I want to think of a transformation of the set of basis vector coordinates, oh, sorry, set of basis vectors, forget about the word coordinate, shouldn't be here, right? It cannot be the same as the transformation law of the components of the vector, right? It has to be different, right? But note the subtlety. When I speak transformation law of a vector, I mean the transformation law of the components of the vector. And when I speak of transformation law of the basis vectors, I mean the transformation of the set of 4 basis vectors. It's not the same thing. Okay? Okay, so what is transformation law of the set of basis vectors? Right. So again, I have a vector V, which I can write as a sum of components in a given basis. So it's sum from mu equal 0 to 3 of V mu, E mu. Again, V mu are the components of the vector and E mu are the set of 4 basis vectors. Right? Now, when we make a transformation from one coordinate system to the other, what happens to the vector?
Vector itself, nothing.
Nothing, right? What changes are just the components of the vector, right? So let's see how that reflects in the transformation law of the set of basis vectors, right? So I can write it down. If I write V equal V mu E mu, right? Then in different system, it will be V mu prime E mu prime. But I know how V changes, right? V nu prime just lambda nu prime mu v mu e nu prime. Because this is the transformation law of the component of the vector, right? This is always true, right? Regardless of what exactly values for v mu we chose, right? So it's true for every v. So we can always, since this is always true, then it means that E mu is lambda mu prime mu E mu prime. Okay, so, you know, we have the old basis. This is without the primes, right? So this is the old basis. This is the old basis. And this is the new basis. But of course, we want to know how the new basis do. So we have the old basis in terms of the new basis. We want to transformation to get the new basis in terms of the old basis, right? So what do? We have to multiply that by an inverse of the Lorentz transformation, right? We have the old basis as a Lorentz transformation times the new basis. So to get the new basis, we need to get the inverse of the Lorentz transformation. But what is the inverse of a Lorentz transformation? What is the inverse of a Lorentz transformation?
A Lorentz transformation.
Exactly. It is by itself a Lorentz transformation, right? So that's why we're going to introduce a slightly subtle notation. Again, this varies from different textbooks, but we're just going to use as an inverse Lorentz transformation. We're going to write down as a lambda minus 1 nu prime mu. I'm going to write as lambda mu prime and mu. I put the mu prime as a subscript and the mu as an upper superscript. All right, it's a bit subtle, right? I just switch the upper and the lower. So now we can write down E mu prime as lambda mu prime mu. This is the inverse Lorentz transformation times E mu. Now, of course, what we really have here, right? We can use this to write it down as lambda mu prime mu, lambda sigma prime mu. There's a what? It's a transformation times its inverse.
Delta function.
Exactly, just a delta function, sigma prime, mu prime. Note that with a delta function, I can't put the indexes one on top of the other. It's either 0 or 1. And then, of course, lambda mu prime mu, lambda mu prime rho is just a delta mu rho. Right, that's the standard conical delta symbol. I believe you've seen that. Right. Now, I put myself a note. In the textbook by Schutz, he uses a slightly different notation than the one I use here. So when you read this textbook, have attention, pay attention to that. Okay? Yeah? Very quiet. Too quiet. Okay. Now that we got that, not too hard, right? I mean, I think I could say it in 15 minutes or so and then get on with that, rather than spending a whole hour on that. You're not sure, you disagree. Some of you disagree. Okay, right. That naturally leads us to the concept of covariant vectors in the dual space. So the transformation laws of the components of a contravariant vector are different than the transformation law of the set of the 4 basis vectors, which are associated with a given coordinate system.
Sorry, Asaf,
Right.
can I ask a question?
Yes, you can.
So basically, until now, when we learn spatial relativity, we use just Minkowski, and all the transformation kept the vector basis the same, right? So that's why we didn't care, I think, about the basis vectors.
We're not going to care too much about the basis vectors anyway, but we didn't really, the only thing we did so far was defining the concept of an event, the concept of a Lorentz factor, and the 4 vector of coordinates.
Yeah, I mean in second year, like when you learn, or first year, I don't remember, you learn spatial relativity. So you you imagine always you have the same basis vector and you don't really care about them, although there are change in some cases, because in these cases the inverse is the same as the transformation itself.
I don't think you have the same basis vectors. No, you may not have thought of that, but when you spoke in first year, right, you made the Lorentz transformation from one observer to the other. You have changed the basis vectors, right? T prime and X prime, right? You didn't think about rotations, but you did do boosts. And you did change the basis vector representing T prime and X prime. They're not the same as T and X. You just didn't call it like that. Now I'm actually calling it. I told you, we are putting up the carpet and we're wiping the dust behind one by one. We're going to need that.
Okay, thanks.
But to have a precise definition of the things to come. Okay, you did do that, but nobody actually told you that that's what you're doing, or you maybe didn't think of it until now. But that's exactly what you did. Now, you didn't think about inverse transformations, I assume, but we'll see in a second why you didn't think of it and why we do need to think of it right now. Covariant vectors in the dual space, right? So we just said that the transformation law of the components of a contravariant vector are exactly the opposite, or are different than, should be careful in what I say, than the transformation law of the set of basis vectors, which are associated with the given coordinate system. That's why I wrote down the basis vectors with lower indices. Right, and just show the transformation. They transform according to the inverse matrix. Right, and we did that to ensure that the vector itself remains unchanged when we change the basis. But we can think of other objects, right, whose transformation laws would be the same to the transformation laws of the basis vectors and not the opposite. They're not going to be the coordinates of a vector, but something else, right? So once we have a vector space, right, we can think of other objects, right, which essentially will form another vector space, which has the same dimension, but is different. Now, I'm sure that you've seen that in your linear algebra, right? Again, I'm talking about a space that is composed of objects which transform not opposite to the way we transform, whose components will transform not the opposite way to the transformation law of the basis vectors, but the same. How do we call this space? This is the dual vector space, right? Now you have seen dual vector spaces in linear algebra course, right? You have seen. I know you've seen. Now you may have not understood it properly, and that's perfectly fine. I did not understand it properly myself when I was a first-year student. Now you will understand it properly. Okay, so if TP is a tangent vector space, then the dual vector space to it is known as the cotangent vector space. Right? So to each vector space, TP, there is a dual vector space. Right? Known as the cotangent space. Which we call it TP star. The concept of dual spaces, you've seen it in your first year algebra, and you're seeing it now. Okay. What, if you've seen it, let's see if any of you can refresh your memory. What are the objects that live in the dual vector space? Who lives there?
I maybe remember some functional who take your vector to something, but
okay, you're not bad. You're not bad. What is a functional? You didn't even say. When you said when you said functional, you answered. But what is a functional?
That's the problem. I remember the word, I don't remember the properties.
The word, but you don't remember what it means, right? Okay. Right. A functional, basically, it's a linear mapping. The object that you have there, right, is a linear mapping from the original vector space to R. In quantum mechanics, it will be to C. Okay? Namely, you get a vector. You think of it as in terms of a box. Many people don't think of it like that, right? Actually, it's not a functional. Sorry, you confused me. You can think of it as a function more. No, sorry, function is also not the right thing. I have to think if it's a functional or not. Basically, it's a box. It gets a vector, gives you some number. So the dual vector space consists of linear mappings between TP and R, real numbers. Right? So if omega is an object that lives in TP star, right? Omega belongs to, right? It's an object that lives in TP star, right? Is a dual vector. Right? It's really a mapping, linear mapping, namely omega that acts on a vector in TP, well, a linear combination of vectors in TP. So AV plus BW is equal to A is a number, V and W are vectors in TP. A times omega that operates on V plus B times omega that operates on W, and that belongs to R. That is a real number. Okay. Now, these objects, abstract objects, right? They themselves, right, form a vector space, right? So the set of these objects form a vector space. Namely, if omega and eta belongs to TP star, right, then A omega plus B eta that operates on a vector V, pay attention to how I describe it, right, and how I write it, is equal to A times omega that operates on V plus B times eta that operates on V.
So if I define a dot product, the vector space itself can be its own dual space because I can...
Wait with dot products. We'll get there. Wait, we'll get there. Likely you'll have to wait until Thursday, but we'll get there, given the time. One step at a time. Okay. Now, for the set, now I'm looking at objects in the dual vector space, in TP star, right? Now we can now form a basis of dual vectors, right? So we can produce a set of dual vectors of basis dual vectors, which I'm going to call it with a theta nu. Where am I going to put the index, the Greek index nu? Upper or lower? Index? No, upper index. The set of basis for the TP, for the vector space, I put with lower index. Now this is the set of basis vectors for the dual vector space, so I put it with upper indexes. Right? Now, in order for these vectors to form a basis, what would be their operation on the basis vectors of TP? What happens to that vector basis when for these basis vectors when they operate on the basis vectors of TP? What will we get? What do we get?
Delta function.
The delta function. Thank you very much. Right. That's why we don't really need these basis vectors. When you think of it slightly more, it will take you time to digest everything I'm saying, but you realize we don't really need them, right? So similarly to any, to normal vectors, we can, every dual vector we can write in terms of its components, right? So any dual vector, we write in terms of its components in a given basis, right? Can be written in terms of its components in the dual space. Right? Omega mu times theta mu. Now, elements of TP star, the dual space, they're called covariant vectors. We had contravariant vectors. These are elements of the tangent space. Now we have covariant vectors, element of the dual space. They live in different worlds. They don't belong to the same space. You cannot add them together, but they can operate one on the other. Right? Now, the covariant, because they transform the same way as the coordinate that we had. It's the same Lorentz transformation. That's why it's a co. Contra means the opposite. Make sense, huh? Everything will make sense at the end, believe me. Perfect sense. Now, there is another name for these. These are called one forms. One forms. One forms, two forms, are P forms, and there's a whole theory about it. I don't know. Have you did any of you here studied differential geometry? Did I see a yes? I don't see. I don't see all of you at the same time because I see small. If we have time, we'll make towards the end of the course. I may give you a few lectures about P forms and that. There's some quite nice things. You can get Stokes theorem and other cool things, pretty much for free, after you get the theory. But it's not crucial. Now, since we can use this with components, then we can look very simply what happens at the operation of a one form on a vector, right? So what happens when I personally, I may, even without noticing, I may change the wording that I'm using. I may use one form and I may use covariant vectors or a dual vector. It's the same, okay? So the action of a one form on a vector, the action of a dual vector on a vector, omega v is omega mu v nu, sorry, right, theta mu e nu. Again, I write it in components. Omega mu is the component of the one form. Theta is the vector basis. So the vector basis operates on the vector basis of TP, that's E. And V nu is just a component, right? So this is just omega mu V nu, and that's just a delta, mu nu. This is just omega mu V nu, which belongs to R. That's exactly the reason why we don't really use the basis, right? Because it's enough for us to look at the components and that's it. We don't really need to go through all this process of expanding it. We know that the components, they give us everything we need. Okay? But because of that, if omega operating on V is just omega mu V mu, which is some number, then we can think of it, you know, we can think of vectors themselves as linear mappings of dual vectors into R also, right? So V, this we can think of vectors as linear mappings of dual vectors to R. V of omega, I'm going to define it as omega that operates on V. It's just omega mu, V mu. What did I just say? I just said that what is the dual space to the dual vector space? What is the dual to the dual?
The vector itself.
The vector space itself. Right? So just to say that the dual vector space to the vector space itself, dual space to the dual vector space to the dual space is the original vector space. What would be the transformation law of the components of the dual vector? Sorry, of the components. What's the transformation of the components of a dual vector?
The same is for the vector with the inverse.
The inverse to that of the vector. It's not the same, exactly the opposite.
I mean the same as for the coordinate.
Same as the coordinates, very good, right? So omega mu prime is just lambda mu prime nu omega nu, right? It's covariant. It's the same as the coordinates. And for the basis, theta,
the same as contravariant.
very good. Lambda rho prime sigma and theta sigma. Right. Now this transformation, by the way, right, ensures that, you know what, this guy here, what is that? This object here that I just marked, what is that? What type of object is that?
Scalar?
It's a scalar, right? It's just a number, it's a scalar. So how does it transform under Lorentz transformation?
Stays the same.
Stays the same, right? It's invariant. Right? We have two Lorentz transformation, they cancel each other. It's invariant. So a scalar, this notation really ensures that the scalar is invariant under Lorentz transformation. Right? Okay. Example. Now I'm going to tell you, I'm going to surprise you. You've all seen that and you're working with all these things, but you may not have called them like that and you may not have thought of them like that. That's the right way of thinking of these things. So, how do we normally write a vector? If you have to write a vector, I have to write a vector. How do I normally write it? I already wrote you a vector, right? How do I normally write it? Maybe my question is not exactly clear. If I ask you, okay, please write me a vector.
I do a parentheses and then write numbers.
It's a column, right? I write this a column, right? So if I write a vector v, I'm going to write this v1, v2, vn, right? That's the regular way of writing a vector. then what is the regular way of writing a co-vector or a dual vector? Right, in n-dimensional space. How would I write a co-vector?
In a row.
In a row. I told you you've seen that, right? You just didn't think of that all the way. And how am I going to describe the action of a dual vector on a vector?
Dot product.
Because it's just a multiplication. It's not a dot product because we haven't defined a dot product yet. It's slightly more complicated than that, but just to give you the feeling that you know what I'm talking about, even though it was very abstract, right? This is just going to be omega 1, omega 2, omega n, multiplied with the regular way that you did multiplication so far. V1, V2, Vn. This is just omega I, Vi. Right? Sum over I. Yeah? Now it makes sense, huh? Everything makes sense. Just the way it is. That's the same way that you've been taught in first year linear algebra. Just putting it in a, basically it's a review. I'm not saying anything which is really new. I don't know why some of you don't open your cameras, though I ask you to do that. Maybe you can't, I don't know. Right. Another example, which I believe is familiar to you. A bit more abstract, but essentially from a mathematical point of view, it's exactly the same. You've seen in quantum mechanics, right? Now we're talking about vectors in Hilbert space. How do we represent a vector in Hilbert space?
Bracket.
Right, bracket, right? A vector in Hilbert space is a cat. Dirac notation. Right, a vector in Hilbert space. Noted by a cat. And so a vector in the dual space will be denoted by a bra. Dual space, vector in the dual space. Will be a bra, right? And what is the action of a vector in the dual space on the vector in the tangent space? What is that?
The multiplication.
That's a bracket, right? By psi. And what is that? What is it, the bracket? What does it give us?
Inner product.
Forget about inner product. We haven't defined an inner product.
A complex number or
This
real
is a complex number. This is, yeah, exactly. This is a complex number. This is just a complex number. So in quantum mechanics, it's a complex number, not a real number. Here it's easier. It's just real numbers. Right? The idea is the same. And the last thing I'm going to say, there is one object in physics which is a dual vector, which you know it very well, but you never thought of it as a dual vector. The object is the gradient of a scalar function. The gradient of a scalar function, right? D phi, right? What is that? It's a set of partial derivatives, right, with respect to the space-time coordinates. D phi over dx mu theta mu. Now I argue that this is not a regular vector. Just to think of the gradient as a vector, it's not a vector. It's a covector. It's a covariant vector, right? You can do that by using the chain rule. To switch coordinates. D phi over dx mu prime is just dx mu prime over dx mu. Sorry, the opposite, exactly the opposite, right? It's dx mu over dx mu prime, d phi over dx mu. But dx mu over dx mu prime is just the inverse Lorentz transformation. So the gradient in the new coordinate system is related to the gradient in the old coordinate system by the inverse of the Lorentz transformation. Sorry, the components of the gradient in the new frame is related to the components of the gradient in the old frame by the inverse of the Lorentz transformation, which means it's a dual vector. And that's why we're going to use a short notation from here on. So short notation. D phi over dx mu, I'm going to write as d mu phi. And I might be doing that without even paying attention to what I do. It becomes automatic. And another way is phi, comma, mu. We're going to use this notation from here on. You sure this is just because I want to confuse you? And you're right. But when you start writing things fast, it will come out very naturally. X mu has an upper index, but the denominator of the derivative means that there is a lower index on the object because X mu with the upper index appears in the denominator. Okay, just last thing before we go home. Okay, maybe I can skip that for now. I gave you too much. Not too much. I gave you a lot to think of. Listen, I told you that this course is going to be a lot of math, and then there'll be a lot of physics. You're going to work hard for the math, and then a lot of the physics will just come out like that. You just follow the math, and it will just go like that without even noticing. The reason why I'm spending I spend a whole lecture on that, because this is damn crucial. Because without that, you can't really understand the next thing, which will be to define tensors properly, which we're going to use all the time from here on. Again, at the end of the day, you'll find out that what we did is very straightforward. We spend a lot of time saying things which you've been using, you sort of know, you definitely learned. You might not have paid enough attention, but that's not my responsibility. But now is the time to pay attention to all these subtopics, okay? Because they're all here and they're important. Okay, I told you, make sure that you're with me. Next time we'll do tensors and we'll do, and then we'll start do physics. And you'll see that after we go through all the math, the physics will be very, very simple. But make sure that you review the things, and if something is not clear, then you come and ask. I'll also give you your first problem set, I think, next lecture. So you'll start thinking of things by yourself. Any questions before we go? No? Okay. Take it easy. Go back over the lecture. I'll put the, it's been recorded. You get the recording. I'll put them on the course webpage. And make sure that everything is clear. And it's not that hard at the end. It makes perfect sense.
תודה רבה.
Okay? All right. Good.
Bye bye. Good day.
Not have a great